All right, let's go through the processor pipelining practice problems. So the first question here was about single cycle performance penalty. So we have a bunch of instructions here, type 1, 2, and 3, and we tell you how long each one takes to execute, and we tell you what percentage of the program they are. So we have two questions. What's the fastest clock time for this single cycle processor, and how much of the processor's time is wasted for this program that has these breakdown of instructions? So let's take a look at the first one here. So the clock is limited by the slowest instruction, so 800 picoseconds. So we can't run any faster than this instruction or it wouldn't be able to finish. So that means the fastest clock speed is 800 picoseconds or 1.25 gigahertz. Okay, so that's the fastest we can go. Now how much of the processor's time is wasted? Well, whenever we do these type 2 instructions, we know we're going to waste a lot of time because we have 800 picosecond clock cycle, but type 2 instructions only take 200 picoseconds. So we're going to waste 600 picoseconds here, and we're going to waste that 20% of the time. Do the same calculation for the other two. So 30% of the time, when we do type 1 instructions, we'll use all of the time because we need it to complete them. 20% of the time over here, we'll use only 200 of the 800 picoseconds of the clock cycle. So we'll waste a whole bunch of time. And then 50% of the time for these last instructions, we'll only use 250 out of the 800 picocycles. So we can calculate what this is. It's just the amount of time we do the instruction times how much we're using or wasting added up. So we're using 51% of our time here, which means we're wasting 49%. So if we have a single cycle processor, the processor has to run as slowly as the slowest instruction, and for this program and these instructions, we'd end up wasting 49% of the time because 49% of the time we're doing one of these instructions that doesn't need a whole amount of time of this instruction. All right, so here's another part of this question. In a multi-cycle implementation, the cycle time of 100 picoseconds, how much time is wasted? So in a multi-cycle implementation, we're going to take each of these instructions and we're going to divide them up into 100 picosecond blocks. So this instruction here, well, it's 800 picoseconds, so we divide it up into 8 cycles. So when we divide up into 2, this one's a little harder. We can't divide this up equally by 100 picosecond cycles. So the first thing to do is look at these, how many cycles are they going to take? So the first type of instruction, type 1 here, is going to take 8 cycles to complete because it's 800 picoseconds, so we have 100 picoseconds per cycle. The next one's going to take 2 because they were 200 picoseconds. And the last one is going to take 3 cycles because we need 300 picoseconds to finish this here, but we're going to waste a bunch of the time there. So you can see over here we're going to waste 17% of the time because for 50 of the 300 picoseconds we're going to have to use for this instruction, we're not going to be doing anything. So type 1 and type 2 aren't going to waste anything, but the last one is going to waste it. It's going to waste 50 picoseconds every time because we need 3 cycles, sort of rounded up things by saying everything's going to be in 100 picosecond chunks. So for the mixture we have here, we can just add them up, how much they waste times the amount of program we get, and we can see that we're going to waste about 2% of the program in total. All right, now we have a question about determining branches. So the first part of this question is, where is the branch determined? Second part is, draw out what happens when the program executes the following instructions. A, B, branch equal F, C, D, E, F. Sorry, this should actually be branch equal G here. We'll see in the solution. When it's run and when the applicant branch is taken. So we're going to do A, B, branch equal G, and then we have the rest of the instructions in the program. And we're going to take a look at that in this pipeline diagram here. So here's instruction A, starts out in cycle 0, and it's in the IF stage. In cycle 1, it moves on to the ID stage, EX, MEM, etc. It goes through the pipeline. You're going to get to fill in the rest of these. So what happens with instructions C, D, and E? Is this what we want? And finally, if you could squash an instruction, would that help? So let's take a look at the solution. All right, so which stage is the branch outcome decided? Well, it's decided in the memory stage here. You see here we get the result of the add, and over here we see whether that result is 0, and we send it back to choose the next instruction. So what happens when the program A, B, branch equal G, C, D, E, F, G is executed and the branch is taken? So let's take a look at this. So we're going to execute B in the next cycle because we're going A, B. B is going to go ahead through the pipeline. Then we're going to execute our branch equal. So now we've executed A, B, branch equal, and our branch equal is in the pipeline. Now, on cycle 3 here, branch equal moves over, and it keeps going through the pipeline, but it's not until cycle 5 here that we actually know which branch to take. So in cycle 3 here, we don't know whether we should take the branch yet. So we're going to go ahead and execute the next instruction, C. And then on the instruction cycle after that, we're going to execute D and C. And then finally, E, D, and C are going to be in the pipeline. So it's not until down here in cycle 5 that we know what the next instruction is, and we can go over here and tell the instruction fetch, no, really go and fetch G. Because we wanted to do A, B, branch equal to G, but instead we ended up executing C, D, and E instead. Once we get to here, we've got these instructions in the pipeline. And what happens is they just move through the pipeline. And you can see over here, instruction C is about to start writing back and saving its results. So what happens to instructions C, D, and E? Well, they execute. Even though we don't want them to execute, because it takes us a long time to figure out if we should branch, they go ahead and execute. Is this what we want? No, it isn't. We want it to jump directly to G. We want it to go A, B, branch equal, and then G, not execute C, D, and E. So how could we fix this? If we had logic that could squash them, this would help. So we could say, hey, we did a branch, and the branch wasn't where we expected to go, so let's go ahead and kill these instructions. And if we could do that, now we're going to execute the correct instructions. All right, so now let's talk about branch delay slots and keeping the pipeline full. So here we've got a table which has the number of branch delay slots and the percentage of branches. Then over here we've got the number of no-ops over the total number of instructions, and then we're computing the number of useful instructions over the number of instructions, and from that we'll calculate the percent of no-ops and the instructions per cycle, assuming we can do one every cycle. So let's take a look at this first row here, where we have one branch delay slot and 10% branches. So in this case, every 10th instruction, we're going to have a branch. That means every 10th instruction, we're going to have an additional delay slot. So how many no-ops do we have? Well, we have one no-op for every 11 instructions. So that means 10 out of every 11 instructions are useful. So 9% no-ops, or IPC goes down by 9% to 0.91. Now when we have 3 branch delay slots 10% of the time, what we're going to see is we have even more of these. So every 10 instructions, we have 3 no-ops. So that means 3 no-ops out of 13 instructions total. So 10 out of 13 instructions are useful, 23% no-ops. That's looking awfully high. So now our IPC goes down to 0.77. And you can go through and calculate this for these other ones. If we have 3 branch delay slots and 50% branches, our IPC is down to under half of what it was before. So question here, is this performance loss for the first one up here, the least bad one up here, is that acceptable? So is losing 10% performance okay? And the answer is no, 10% performance is terrible. So what processor designers do is they figure out how can we go ahead and get rid of these branch delay slots if we can't fill them. Now let's talk about filling branch delay slots. So here's some code, and we've got a bunch of branch delay slots in here. So we're doing some addition, some subtraction, then we're doing this branch. Then we put in 3 branch delay slots here because we've got all these delay slots. We can't do anything here because we have to wait for the branch to resolve. So can we change the way the code is written here to get rid of as many of these or to do something useful there? So let's take a look at this. Well, we need this first add-I here because we're going to use the add-I in the branch. So we can't put that in the delay slot because it has to happen before the branch. Then we can go ahead and do our branch here, and we can take these other instructions that aren't affected by the branch and we can put them down lower. So we took this add-I and the subtraction and we put them down here after the branch because we don't need to do these before the branch. So these are always going to happen. So since these are always going to happen, we can put them in the branch delay slots and they'll always happen whether or not we take the branch. Now we only have 2 instructions to put down there, so we're going to still have to have a no-op. And then finally, our last instruction here is where we jump to on the loop. Our last instruction here we need to wait for because we need it again for the loop. So we can go ahead and put in our no-op here, and now we've managed to take these 2 instructions that are always executed depending on the loop, and we put them in the branch delay slots where we know they'll always be executed regardless of the loop. Here's a question about infinite pipelining, or well, getting towards infinite pipelining. So we're going to look at calculating the throughput latency, the energy used, and the energy and throughput increases for different amounts of pipelining. So we've got an instruction, takes 100 nanoseconds, uses 100 picojoules. We've got a pipeline register that takes 2 nanoseconds and 2 picojoules. If we have a pipeline depth of 0, that is no pipelining, then we'll get a result every 100 nanoseconds because it takes 100 nanoseconds to compute our instruction. Our latency is 100 nanoseconds. Our energy is 100 picojoules just for the instruction, and we've got our baseline energy increase of 1, since that's where we're starting from. What happens if we have a pipeline depth of 2? So now we've got 2 stages in our pipeline. Well, now it's going to take 52 nanoseconds for each result. Why is that? Well, we're going to take this 100 nanoseconds for the instruction, divide it in 2, but then we've got 2 nanoseconds for a register, so 52 nanoseconds for a result. Our latency, that is how long does it take each instruction to do, is going to be 104 nanoseconds. So we have 2 pipeline stages of 50 nanoseconds and 2 pipeline registers. And our energy is also going to be 104 picojoules because it's 100 picojoules for the instruction, plus we've got 2 pipeline registers, so 4 picojoules for that. So what we see here is our throughput's increased almost by a factor of 2. We went before from taking 100 nanoseconds for each result to almost 50. Our energy is only increased by 4%. What happens if we go up to a pipeline depth of 10? So if we go to a pipeline depth of 10, we're going to go up significantly in our throughput. So here our throughput is 12 nanoseconds. We've taken our delay, divided into 10, so each instruction takes 10 nanoseconds, each pipeline takes 10 nanoseconds plus 2 for the register. So if our pipeline is full, we get one result out every 12 nanoseconds. However, each instruction takes a long time to go through. It has to go through 10 pipeline stages, just 10 of these are 100 nanoseconds, plus 10 pipeline registers, so another 20 nanoseconds here. So now our latency for each instruction has increased. Our energy is also increased. If we go up to a pipeline depth of 100, we see it's taking 3 nanoseconds for a result in throughput. And why is that? Well, we've taken our delay here, divided it by 100, so it's now 1 nanosecond of computation for each stage, plus 2 nanoseconds of registers. Our total latency, how long does each instruction take, has gone way up, because now we have 100 nanoseconds for computation, plus 100 pipeline registers. That's 100 times 2 nanoseconds plus 100, 300 nanoseconds. And our energy's gone way up because of those pipeline registers. So we've had a huge increase in throughput if we can keep our pipeline full, and a big increase in energy. So, is the throughput increase worth it in terms of energy for a server device or mobile device? Well, for a mobile device, definitely not. You can't afford 3 times as much energy. Even for a server, you can't afford 3 times as much energy. So even though we could run our throughput 33 times faster if we did all this pipelining, the energy increase is going to make that very unlikely that we'll decide to do that. Now let's take a look at control. So here we've got our pipeline register, and let's take a look in each of these stages what some of the control signals are for a bunch of different types of instructions. So for the add instruction, what happens? Well, it's an R-type instruction, and in the execute stage, what are we going to do here? So the ALU source is going to select the register file. Because we're doing add, so we need 2 register values. The destination register here is going to be selected as the RD register, so we can write it back into the right place, because it's an R-type instruction. We have 3 registers. And the ALU operation is going to be an add. So that's what the control bits are going to do in this part of the stage. Now in memory, the add instruction doesn't do anything. So we're not going to branch, we're not going to write to memory, we're not going to read to memory. When we get to the write back stage here, our memory to register register here is going to select the register value. We're not reading from the memory. And are we going to write to the register file? Yeah, we're going to write to the register file because we want to write the data back. Now let's take a look at load. So load is an I-type instruction. So when we get to the execute stage here, we're not going to select the register file here. We're going to select the immediate value to add to calculate our offset. We're going to do an add here as well. And for writing the result back, we're going to put it into the other register, the RT register, because it's an I format instruction. We only have 2 registers in our instruction. Now when we get to the memory stage, since it's a load, we're going to say read is true. And when we get to write back, we're going to select the memory input to this mux because it's the memory value that we want to write back to the registers. Now how about branch not equal? Well, this is also an I-type instruction. So for branch not equal here, we're going to take 2 register values because we need to subtract them to see if they're equal. For the register destination here, well, we don't care because we're not writing anything back, and the operation is going to be a subtract as we're doing a branch not equal. For memory over here, we're not going to memory read or write, but we are going to set the branch to be a true so that we know to calculate the branch and we can go ahead and update the PC. In write back, we don't care if we select read data or the register value because we're not writing anything back, and in fact our write register here is going to be 0 because we're not writing back to it.